Welcome to this video. We are going to take a look at some circular motion problem scenarios. We're not going to solve them, we're just going to show the setup. Now, every single one of these problems involves essentially the same procedure. We'll be using this equation, and we'll be plugging in for the net force by inspecting our free body diagram. So if we look at this object, or this scenario, we have a puck moving around a table. There is a hole cut in the middle of the table, and a string connecting to the puck loops through the hole, goes through the table, and connects to a block. This block is hanging freely. The floor is down here. It's not touching the floor, so there is no normal force. What are the forces that act? That's the key. Draw free body diagrams so that you know what to plug in for net force. Okay? Well, the puck feels a gravity force, but it also feels a normal force, preventing it from falling through the table. Is there anything else touching the puck? Yeah, there's a string, and anytime we have a string, tension pulls, force of tension, pulls back in toward the center of the string. But this block is hanging at rest. And also, we should note, wherever you have one tension force, there is a second tension force at the other end of that string. Because the block is hanging at rest, its gravity force must be exactly equal to the tension force. Ft equals big M, the second block, times 9.81. Now, if this tension force is big mg, so is this one. And if we cancel out normal force and gravity, the net force is force of tension, which we could find from big mg. So that's essentially how you solve this problem. You get the speed by solving for tension force first, plug in the mass, then plug in the puck's mass and its radius, but convert to centimeters, from centimeters to meters first. That's the solution. It's also worth pointing out, the reason right here we use the puck's mass is because the puck is the only object traveling in a circle. And when you look at the puck and you say, oh yeah, it's traveling in a circle, therefore the net force is always going to point toward the center. Is that true for the puck? Yeah, here it is. That's the net force, tension. Tension is the only unbalanced force, so that's the net. Okay, on to the next one. You've got a ball swinging around a circle at uniform speed. This is outdated. And here is the ground below. So the ball's not touching the ground. And there's people watching. Maybe someone's holding this with their hand, swinging around. But it's, this is up, down. This is vertical. Here's a tree. Okay, you get the idea. We are oriented. So in this kind of a scenario, what forces act on the ball? Well, gravity pulls the ball downward, right? Is there anything else touching the ball? There's no normal force because it's not touching the surface, but it is touching a string, so there's a downward force of tension as well. What we can do again is write the equation mv squared over r, but plug in for F net. We have two forces, they both point in toward the center, so they are both positive. To find the speed, we're looking for tension. So to find speed, and we know everything else, we know the mass, we know g, we know r. The only thing we have to find first is speed, and we get that from 2 pi r over the period, the orbital period. And in the version of this question that I gave you, it said something like it makes one revolution every 0.333 seconds. So that 0.333 seconds, the time for one revolution, that is the period. So we solve for tension. Part B is the same scenario, it's just the ball has reached the bottom. Is it going faster? Well, normally you might think that this gravitational potential energy converts into kinetic, but the person is holding the ball and swinging it to keep it moving at constant speed. They say that right here. So the speed you found in part A is the same as part B. Same speed in part B. Okay then, let's draw the forces so that we know what to plug in for F net. There's gravity again, of course. But there's tension as well, because there's the string still connected. So the question is, does tension point smaller, like this, smaller than gravity, equal to gravity, or bigger? Before you answer, remember, it's moving in a circle. The net force has to point toward the center of the circle. Therefore, tension must be bigger. Tension must be bigger. So that when you canceled out some of mg, you'll have a little bit left over here, causing the net force to point in toward the center, thereby turning the ball. Okay, so let's plug in our forces. Tension is positive because it points in. Mg is negative because it points out of the circle. And you plug in and you solve. Solve for tension. Number 3, you got a car moving around the road like this, and you were looking at it from above. So pretend for a second you're standing here, watching the car kind of coming at you there at that moment. So what do you see? Well, here's the road. Here's the car, the front of the car. And like here's the license plate and the windshield. And if the car kept going around, eventually it would be here, and you'd be looking at the back of it. You know, it's like here's the gas, the exhaust. So it's turning around like this, kind of. That's the idea. Okay, at this moment, shown on the left, there has to be a net force pointing toward the center of the circle, which is this way. Where that force comes from, we'll take a look at that. But first, let's point out we also have gravity, and we have normal force. What's this force? Well, let's, just to help us think through, think about the fact that if the road were wet, the car wouldn't make the turn. This force would not exist if the road were wet. Also consider tires are made of rubber so that the car has grip. It's the grip, it's the traction that allows the car to turn. You're probably starting to surmise that this is the force of static friction. And in these problems, we'll always be dealing with static friction at a maximum. Okay, so the net force has to point toward the center. Therefore, Fs max must be the net force. It must be, in other words, mv squared over r. Okay, that means these forces must cancel each other. Fn has to equal mg. We can plug in for the friction force using the equation mu times the normal force. But Fn, we've just written down, equals mg. Whoops. So the right side stays the same, mv squared over r. But notice that we can cancel, we could divide both sides by mass, and that would cancel out the masses. Number 4 is the same. And so is 7. No, which one? 9 is the same as well. 9 is the exact same situation. You have static friction pulling the fly in. Normal force and mg, they cancel. Same exact situation. Okay, number 5. Here's another one where the ground is down here. So then there might be, a person standing, kind of watching all this. And a tree. It's a weird looking tree. Okay, but the point is, the ball here is not touching the ground, so again, no normal force. It is pulled by gravity, and there's a string, so it's pulled by tension. And let's draw those forces again. Here's the tension force, a little bigger. Here's the gravity force. And anytime you have a force at an angle, we like to draw components. Let's call that Fy and Fx. This angle is 30, the problem says. So, and to prove it's 30, by the way, you have a vertical line here, a vertical line here, and a single bisector. So those are alternate interior angles. That angle right there and that angle right there. alternate interior. Okay. Now we can squiggle out of the hypotenuse because we've resolved that vector. We've shown its components. So what's the net force? Well, here's the center of the circle. The net force has to point to the right. That means Fx, the x component of tension, is the net force in this problem. And how about Fy and Mg? They must cancel out. So you can find Fy because we know mass and we know gravity, 9.81. If you look at the tangent of the angle, the tangent of 30 degrees, tangent is opposite, that's Fx is opposite, over adjacent, which is Fy or Mg. So that's our process. You can plug in Fy. Let's write that as Fy. We know Fy because we found it from Mg. So we could calculate Fx, plug it in here, and solve for the speed. Number 6, last one. In this problem, we have a cart moving around a track on a roller coaster. So, okay, we know gravity is acting. Same game, right? Same thing as always. F net equals mv squared over r. Draw your free body diagram, and then plug forces in for F net based on what you see in your picture. So what would we see? Okay, there's gravity pulling down, and there's normal force pointing up. So is normal force, is it smaller, equal to gravity, or bigger to the gravity force? Remember, the net force must point toward the center. Well, wait, the net force has to point down toward the center. That means normal force is weaker, and gravity is stronger. So it looks like this. On a test, if you get this question, make sure you draw the normal force shorter at the top. Okay, mg is positive because it points into the circle. Fn is negative because it points out of the circle. When we add those two forces, we get this. They gave us the speed at point A. We know the radius of A, it's 18. We know the mass, we know g, so you can solve for the normal force at A. Okay. Part B. Similar kind of setup. We know we're going to use this equation. We're finding the normal force. We have to use the speed at B and the radius at B. Okay, speed at B. Well, let's come back to that, mv squared. First, let's draw our force diagram to see what forces act. Of course, always there's gravity. But there's also the normal force because the car is touching the track. It's touching a surface down below. So is the normal force smaller, equal, or bigger? The net force, when you add these up, there has to be more. The net must be pointing toward the center. That means the normal force is bigger. It's like this, perhaps. That's not quite bigger. Let's try that again. When you add these up, normal force is positive because it points into the circle. Gravity is negative because it points out of the circle. We know the radius, right, 31. We know the mass. We know g. But we don't actually know the speed yet. We're trying to find normal force. So before we can solve, we will have to first find the speed at the bottom at point B. How do we find the speed? Well, at A, there is some energy, and that total mechanical energy is conserved. It's equal to the value at B. How do I know? Friction is negligible. So what energies do we have at A? It's moving, so there's 1/2 mv squared. There's height, so we have gravitational potential energy. And at the end, at B, all we have is kinetic because the height has all disappeared. If you divide both sides by masses, you would have to distribute that to the two terms on the left, and all the masses cancel on the left. And when we divide the right side by mass, guess what? Mass cancels there too. So you end up with 1/2 of the speed at A squared, that's 12, plus 9.81 times the height at A equals 1/2 of the speed at B squared. But what's the height at A? Let's see, this is the height at A. Hang on, that's one radius and a second radius. The height is just 18 plus 18, or 36. So you can find the speed at B, plug it in here, and find the normal force. So that's how you solve these problems. We're going to skip 7 and 8 right now, but that's how you solve. Thanks for watching.